Our guest is Dr. Megan Argo, and she is a professional astrophysicist and science communicator. She is a senior lecturer in astrophysics at the University of Central Lancashire in Preston, England, studying galaxies in the nearby universe with radio telescopes. Megan regularly pops up on the BBC to talk about astronomy and space news, stories, and gives public lectures in schools, workshops all over the country. She has over 20 years of experience communicating science to a variety of audiences. Dr. Argo has worked as a scientist in the UK, Australia, the Netherlands, and been lucky enough to observe with some of the best radio telescopes in the world, in Europe, India, USA, and Australia. Her passion for sharing the wonders of the universe with children of all ages has taken her from northern Scotland to Western Australia, India, the mountains of Colombia, and South Africa. What is she doing when she's not teaching astronomy? She is a member of the Girl Guiding. She is an amateur radio operator. We got a lot of those. And she's a samba drummer and can often be found flying kites, hiking, climbing, swimming, cycling, or running. And she says on her webpage, not at the same time. For complete information, and there is more information, you can go to her website at drmeganargo.net, and that's Dr. Megan Argo is one word. And her talk tonight is on predictions for astronomy for the next 200 years. Oh. So Dr. Megan, without further ado, you're up.
That is great. Thank you very much. Right, I will just share my screen and there we go. So hopefully you can now see my title slide.
We can.
Great, thank you. Always worth checking, I found, doing this on Zoom. So good evening, everyone. Yeah, it is Wednesday over here in the UK right now. So if I look a little bleary-eyed, yeah, it's because it's after midnight. So it's a pleasure to speak to you today. As you might have gathered, I first came across the Fort Wayne Astronomical Society because of one of your members, Geddas, and I apologize, Geddas, but I had to show the image that started all of this. So this is actually the title slide from a talk I gave at a conference in 2010. And it was a conference of professional astronomers who were radio astronomers. And the thing with radio astronomy is we have big networks of telescopes that take very, very high resolution images of the sky. But the problem with those images, they are extremely high resolution, milli-arc-second resolution, but we usually only have very, very, very small fields of view. So what I wanted to do was to emphasize to these radio astronomers just the kind of scales that we were looking at on the sky, because most professional radio astronomers are not used to actually looking through an eyepiece at the sky and looking at the kind of objects that most amateur astronomers are used to looking at. So this image was a fantastic illustration of just how big the Andromeda Galaxy was, because the project I've been working on was trying to image the entire of M31 using these networks of radio telescopes, which is just something nobody had done before. It was a really technically challenging project, and I wanted to emphasize just the size of the sky that we were actually looking at with this project. And this image was just a fantastic illustration of that, and Geddas very kindly let me use it and has let me use it ever since in a couple of my public talks. So thank you very much, Geddas, for all of your help there. So it is a huge pleasure to speak to you guys tonight. And yeah, the title of my talk is The Next Blink of a Cosmic Eye, Astronomy in the Next 200 Years. Now, predicting the next 200 years in astronomy is something of a challenge, as you might expect. An awful lot has happened in the past 200 years, and there's an awful lot of course, uncertainty about predicting the future in any area, and astronomy is really no different. So a little bit of context as to where the talk came from. I'm at the moment one of the vice presidents of the Royal Astronomical Society, so the UK's professional body for astronomy. And in my capacity as one of the vice presidents, I was asked in the beginning of 2020 to write a talk as part of our 200th anniversary celebrations. and try and predict what was going to happen in the next 200 years. So we had a talk at one of the meetings in January of that year, looking at the last 200 years of the society. So how the society came into being 200 years ago, when a bunch of gentlemen sat down in a pub in London, basically, and got together and decided that they wanted to form an astronomical society, and it grew from there. So we had a talk giving us some information on how astronomy had changed over that 200 years. And my job was to follow that by predicting what was going to happen in the next 200 years, which is something of a challenge. So I thought a slightly more realistic talk title might be something like this: Utterly Unrealistic Predictions for Astronomy in the Next 200 Years. Because if the history of predicting the future is anything to go by, it doesn't really matter what I will predict. The only certainty is that I will probably be wrong, but we'll have a go anyway. So before we look forwards, then, it is important to have a little bit of a look backwards and see just how far we've come over the last 200 years. Of course, we're not going to spend too much time on this. We could talk for an entire evening just about what's happened in the last 200 years. So a few of the highlights of how far we've come over the last 200 years. There's an awful lot of physics that we didn't know 200 years ago that today we take for granted. A lot of radio amateur operators in the audience. So of course, 200 years ago, we didn't have radio. We didn't know radio waves existed, and there was no such thing as a radio amateur. So a huge amount of we've discovered large parts of the electromagnetic spectrum that we didn't know were there before, and we've actually come up with different tools outside of the electromagnetic spectrum to try and help us understand the universe as well. So some of the things that we're looking at here, we've got the first distance measurement to an object outside our solar system. This is the dwarf star 61 Cygni, the distance of which was first measured by the astronomer Bessel. So this has happened in the last 200 years. 200 years ago, we didn't know the scale of our own galaxy, never mind the scale of the universe. We didn't know how old the universe was. We didn't know that galaxies were all moving away from us. Again, something that we pretty much take for granted now, that the universe is expanding, and there is a lot of evidence that actually that expansion is accelerating, undreamed of 200 years ago. Then, of course, we have the detection of radio waves, which led to eventually the detection of the cosmic microwave background. This is Penzias and Wilson at Bell Labs in the States, where, of course, the first detection of the cosmic microwave background was made. And then more recent history, we of course had the first detection of planets outside of our own solar system, the first exoplanets, going back to the 90s. And since then, of course, the discoveries of exoplanets have exploded. We've now got many more observatories and satellites that are finding exoplanets on a regular basis. So we now know of many thousands of exoplanets out there in the universe. We've also had the first detection of gravitational waves, again, predicted by Einstein 100 years ago, more than 100 years ago now. We actually had the first detections of those back in 2016. And then, of course, just a couple of years ago now, in 2019, we had the first photograph of the event horizon of a black hole. This image down here, of course, from the Event Horizon Telescope. A fantastic collaboration of radio astronomers around the world, linking up telescopes, building new receivers to do a kind of observation that, again, had just not been done before. So the developments, there are so many more that I could have picked to put on this slide, but if you think about what we have discovered over the last 200 years, the progress has been pretty extraordinary. And there is no reason to think that the progress that we're going to have in the next 200 years is likely to be any less extraordinary. So again, some of the other things that have happened in the more recent past that are still sort of ongoing missions, one of the ones I find really, really interesting is the Gaia satellite. Gaia is a fantastic instrument that is giving us a hugely detailed view of our own Milky Way galaxy and the rest of the universe as well. But what it's designed to do is look at the Milky Way, look at the positions and the motions of the stars in our galaxy, and map the distributions and the velocities, and look for the streams of stars as they move around in their orbits around our Milky Way. And this is just a fantastic map. This is 1.8 billion stars in the third data release of the Gaia data, and there's much, much more to come from this data. And this is going to keep astronomers busy for years, if not decades to come. The amount of data that there is coming from these observations is just phenomenal. And this is something that astronomers are going to be looking at for years and years and years to come. There is vast amounts of discoveries yet to be made from data sets like these. And another ongoing project, which is a little older, has been around for a little bit longer. Some of you may remember this launching. The Voyager satellites, of course, Voyager 1 and 2. And these spacecraft have been heading out from the Earth now, out through the solar system, out past the edge of the sun's influence, and out now we think into the surrounding interstellar medium through the bow shock as the sun moves through the interstellar medium. And these things are now moving at quite a rate. They're actually moving at more than 3 astronomical units per year. So since I first gave this talk in January 2020, these satellites have now each moved more than 6 astronomical units further away from the sun than they were when I first gave the talk, which I think is quite mind-blowing. Of course, we don't know how far they're going to get, assuming they don't hit anything, because they could potentially just carry on for forever. Because we don't know what they're going to find in interstellar space. At the moment, they still have something in the way of power on board. That power is diminishing year on year. So the signals are getting fainter and fainter as they get further away, but there's less power to run the instruments as well. So most of those instruments have now been turned off. Eventually they will die, they will stop being able to send the signals back, but they will carry on their travels for the foreseeable future. And my favorite fact about the Voyager missions is that Voyager 2 in 296,000 years will pass within just a few light years of the star Sirius. So if it's clear when we finish and you go outside and you can see Sirius from your back garden, just have a look and think about little Voyager 2 heading off in that direction. Hopefully there'll be the first of many man-made interstellar probes, and that's one thing that I think is potentially probably beyond my lifetime, but I would expect that we will have more interstellar probes at some point in the next 200 years. Okay, so that's a little bit of the history, a little bit of the context. Now the talk is about the next 200 years. So where are we going next? One of the things that I think is really exciting in current times is the advent of reusable rocket technology. This is an image taken from a SpaceX launch and return of the launch vehicle. And that advent of reusable rocket technology is fantastic, not only for the space sector, but for astronomy as well. Because if you can reduce the cost of getting a satellite into space, you can potentially put more telescopes into space, and we can do more science from space than we can today. And again, there are good reasons for us wanting to do that, which we will get to later. But as I said at the beginning, this is something of an ambitious talk. So for a little bit of inspiration, when I was first challenged to write this talk, I did what most astronomers of my generation do when they're looking for a bit of inspiration. They went to Twitter. I went to Twitter to ask for some ideas. I asked my Twitter followers, I said, what do you think is going to happen, or what do you hope is going to happen in the next 200 years? And this is the results of a very unscientific survey of a random cross-section of people who happened to interact with me on Twitter. This is what people said. So this word cloud is made up of the responses that came when I asked, what do you think or hope is going to happen in astronomy in the next 200 years? The bigger the word appears in this diagram, the more times it cropped up in people's answers. So you can see from just looking at this briefly is that people are expecting and hoping that we will either at least look for, if not discover, life somewhere else in the universe. And the most hopeful candidates there, the most likely candidates people think where we might find that are places like Mars. And there are plenty of spacecraft that have already been to Mars looking for evidence of life, and there are several in the pipeline as well. But also places like Enceladus, these icy moons that might have a liquid ocean underneath the thick ice layer at the top. And there are plans to send probes to those sorts of places to drill through the ice and see if we can reach water and see if we can take samples. So that's one of the things people are really looking forward to. A return to the moon and sending people to Mars, again, very, very hopeful that those kind of things are going to happen. We might find out what dark energy actually is, what dark matter actually is, whether dark energy is actually real. That's something a lot of people were curious about. And you can see other things that crop up here as well. Telescopes on the moon, Starlink, a big concern, Starlink being the SpaceX constellation of satellites, of course. So with that in mind, then, what a random cross-section of people who happen to interact with me on Twitter, then what people are thinking about, what are they hoping that's going to happen in the next 200 years? I thought the rest of the talk, I'd look at how the planned missions and projects are actually stack up against people's hopes and expectations for where we're going to go in the next 200 years. And I've selected a few projects that I personally think are exciting, interesting, and worth watching. If you'd asked any other astronomer to write this talk, they probably would have picked different missions and different telescopes because everybody has their own particular interests. So other opinions are available. But what follows is what I think personally are the things that are going to be particularly interesting coming up. One of the things that I think is particularly interesting is a return to Mars. Now, we've got many probes that have been to Mars over the last few years, but what I'm particularly interested in seeing is ExoMars. ExoMars is actually a two-part mission. The first part of ExoMars was the Trace Gas Orbiter, and that's this guy up here. And the Trace Gas Orbiter actually went to Mars some years ago and has been in orbit around the planet for a while now, mapping the atmosphere, looking for details of the gases that there are in the atmosphere. So looking at quantifying the gases that we might only see in small quantities and the kind of gases that might be produced by biological mechanisms. Now, some of those can also be produced by geological mechanisms, which is why it's a two-part mission. If you find trace gases that could potentially come from microbial life forms, then you want a ground mission to go and actually look at the ground and see if you can find any traces of those biological or geological processes to rule out one or the other cause. And that's where the lander comes in. This is ExoMars 2022, the Rosalind Franklin rover, which was due for launch in 2020, but like so much because of the pandemic, it was delayed. So this aspect of the mission is now due for launch this year. It's actually due for launch in September, I believe. And it's going to go up from Baikonur on a Proton rocket. And it's a mission similar to many of the other rovers that have been to Mars. It's going to take surface samples, it's going to drill, it's got spectrometers on board, it's going to look at the rocks and take spectra by looking at the rocks as well. And again, one of the reasons I'm particularly interested in this is it's looking again for those signs of subsurface water, which again, if you're looking for life, you want to look where there are signatures of water, which is one of the things that current Mars missions are also doing as well. Those traces of water are the best places to look for traces of either current or historical life. And my connection with ExoMars goes back to when I was an undergraduate. I was lucky enough to do a summer project at the Anglo-Australian Observatory, as it was then, in Sydney, Australia. I spent 3 months working in the instrument science group. And at the time, this is 20 years ago nearly, they were working on a proposal to the European Space Agency for a spectrograph that was actually going to sit on the masthead here and was actually going to do spectroscopy of the rocks, but actually with a stereoscopic camera. The mission, their proposal didn't get selected for the mission, unfortunately. If it had, my career might have gone in a slightly different direction than the direction it did. But still, this is a really exciting mission that's been a long time coming. And I'm really looking forward to it getting to Mars and seeing what it brings back. There are plenty of other solar system missions on the horizon as well. And another one I think is particularly interesting in the context of looking at exoplanets as well, planets outside our own solar system. And that's the JUICE mission. JUICE is a mission to the Jupiter system that again has been slightly delayed because of the pandemic, but is now scheduled for launch in June 2023. After a 7.5-year cruise phase, it will get to the Jupiter system. And its aim is to look at Jupiter itself and the moons and look at the magnetosphere of Jupiter, the magnetic field, and how it interacts with the magnetic field of one of its moons. It's something that we haven't done before. And it's important in the study of exoplanets because a lot of the exoplanets that we found are big gas giants like Jupiter, and in many cases bigger. So if we want to understand those exoplanets that are comparatively very, very, very far away, it makes sense for us to understand our nearest gas giant in as much detail as we possibly can, which is why JUICE, we're sending a return mission to Jupiter. As you've seen, it's going to do flybys of some of the moons. It's going to do a lot of flybys of Europa. It's actually going to spend some months orbiting Europa, getting close-up photographs of Europa. Then it's going to go and do flybys of Callisto, and eventually it's going to go into orbit around Ganymede and take very, very close-up images of Ganymede. And the reason for interest in Ganymede is it's the only moon of Jupiter that has its own magnetosphere. So studying the interaction of the magnetosphere of Ganymede with the magnetosphere of Jupiter is a unique case. It's something we can only do by looking at the Jupiter system. We don't have anywhere else in the solar system where we can look at the interaction of a magnetic field of a gas giant with the moon, because this is the only case that we have in the solar system. So this is going to be a really, really exciting mission. I think eventually, as you saw at the end of the video there, I can rewind it a little bit. At the end of the mission, what will happen is the spacecraft, as it runs out of propellant, will come in for a grazing impact on the surface of Ganymede. So it'll actually hit Ganymede at the end of the mission. A little bit of space vandalism, but again, on the way down, it will take the highest resolution, the most close-up images we've ever had of one of Jupiter's moons. So even as it comes in for its final stages, we'll still be getting science data back from it. So again, I think that's a mission that's well worth watching. It's going to produce some really, really interesting science. So that's some of the solar system stuff that's on the horizon. Of course, there are lots and lots of telescopes and observatories that are on the horizon as well that are going to produce fantastic results and really help us push forward the frontiers of some of our aspects of science. And one of those, of course, is the James Webb Space Telescope. Now, when I first wrote this talk, James Webb was still due for launch at some point in the future. So this is the first time I've given a talk where I can actually say it's launched and it's working, which is amazing. So this is a little video showing a little bit about the James Webb Space Telescope. This is just the separation from the Ariane 5 rocket. And this is really important because the Ariane 5 launch rocket sent James Webb Space Telescope on its journey to where it is going to spend its operational lifetime. And that Ariane launch, the launcher was so accurate that actually James Webb Space Telescope itself doesn't need as much fuel as we expected for course corrections, which means it can actually last for a lot longer during doing its operations, keeping station around the second Lagrange point, than we anticipated. So we will actually get more than 10 years of operational lifetime out of the James Webb Space Telescope, which is pretty spectacular. So what's it going to do once it gets there? Because the cruise phase, it's on its way to the second Lagrange point at the moment. And as it does so, it's going through the deployment process. A large part of the deployment, of course, has already happened. The big sun shield, the size of a tennis court, has already been deployed. And that sun shield acts to keep the spacecraft cool. This is an infrared space telescope. And infrared space telescopes need to be cold in order to observe the very cool stuff in the universe that they're interested in looking at. You want to bring the noise of your receiver down as far as possible, and you do that by cooling it. And most of the instruments on board the James Webb Space Telescope are actually cooled passively. So this big sun shield separates the spacecraft from the heat generated by the sun and the Earth and the moon, keeps it facing the cold of space, and that the systems on board allow it to be passively cooled down to very, very cold temperatures. There is only one instrument on board that's actually actively cooled, and that's MIRI. And MIRI is actively cooled because it needs to be even colder than the rest of the instruments to do the kind of science that it's aiming to do. So a few facts about the James Webb Space Telescope then. It's billed as the successor to Hubble. It's slightly different to Hubble in many ways. Its development timeline was about the same as Hubble. Hubble was a long time in preparation and development before it actually got to fly. It's the James Webb Space Telescope, half the mass of Hubble, but more than 5 times the collecting area. And that collecting area, of course, means it's much more sensitive. It's different again in that it's working in the infrared part of the spectrum. The Hubble Space Telescope worked mainly in the optical, a little bit into the ultraviolet and a little bit into the infrared, but the James Webb Space Telescope is in the infrared and a little bit into the red part of the visible part of the spectrum. What is all that going to give us? It's going to give us the sensitivity in the infrared part of the spectrum that's useful for looking at things such as distant galaxies, so very, very high redshift galaxies, the first stars and galaxies that formed after the Big Bang. They're really, really difficult to detect. Let's move on. There we go. So this is where the James Webb Space Telescope is right now. I took this screenshot from the NASA website earlier today. So this is the current deployment status. So it's going to let us look at those, hopefully at those very first stars and galaxies that formed after the Big Bang. We know that they started to be created at a certain point in the universe's history, but actually observing them is something we've not been able to do up to this point. And the James Webb Space Telescope with its observational capabilities in the infrared, combined with its big collecting area, its high sensitivity, will hopefully allow us to actually observe those first stars and galaxies for the first time. And that will tell us a lot about how the universe came to be the way that we see it today in the modern nearby universe. It's also going to help us look at star formation and planet formation in much more detail. Again, these processes involve clouds of cold gas collapsing very slowly under gravity. And as they collapse, they slowly start to heat up. And that process you need to watch in the infrared. In the optical, these clouds are dark, they're obscuring, they're thick, the extinction is high, so you can't see what's going on in these clouds in the optical. The infrared is basically the only way we can watch these star formation and planet formation processes happening. So again, that's another thing that the James Webb Space Telescope will really improve, is our understanding of the processes of star formation and planet formation. We know a lot, but there's a lot of unanswered questions in those fields, and the James Webb will hopefully help us answer those. It's also going to help us look for and catalogue objects in the solar system as well. We know of a lot of asteroids and comets in the solar system already catalogued, but we've catalogued the larger end of the population. We know where the big stuff is. The smaller, fainter, darker objects are much, much harder to see. If you've got a big, sensitive infrared telescope, that becomes much, much easier. So one of the things the James Webb Space Telescope will help us do is that sort of space situational awareness of what's around us in the solar system, and potentially which of those objects could come and hit us in the future. Of course, that's a major concern for the future of the planet and for the future of the human race. And the James Webb Space Telescope, again, will help us do that. So its current deployment status, then, you can see here on the timeline, it left the Earth on Christmas Day, and it's now we're on day 24 of the mission. So we're out here. So we're in the mirror deployment stage. So the mirror is now assembled. All the wings have come forward, and it's created the mirror. But what they're currently in the process of doing is actually deploying all the mirror.
Is anybody else hearing anything?
Not a thing.
Looked like she froze up.
There she is.
I'm back. I don't know what happened there, but my Zoom just crashed. Apologies.
Houston, we have a problem.
Indeed. Hopefully the James Webb doesn't. Shall we try that again? Right. Let's do that. And okay, so hopefully we're back to where we were. Yeah, great. Apologies. Let's carry on. Hope it doesn't happen again. Okay, so where were we? Yes, we were looking at the mirror segments. Again, this is a screenshot from the James Webb website earlier today. And this is the current deployment status. So each of these mirror segments is in a particular position, that's the stowed position on launch, and they have to move forwards, only a few millimeters, but they have to be moved forward very slowly over a matter of days. And that's the current process that's happening. They're moving all of those mirror segments to their operational positions. After that, they then have to go through a long procedure where they align all of the mirror segments so that everything is perfectly in focus. And again, that process is going to take a few months while they very, very carefully go through and check everything and make sure that everything is perfectly focused. The last thing we want is a repeat of what happened when the Hubble Space Telescope took its first image and we find that everything is horrendously blurry. That's not going to happen with the James Webb Space Telescope. So yes, I don't know what the first image is going to be. The first target has been decided. They know what they're going to observe first. We don't know what it is in the community. Only a few people know that at the operations center, as far as they know. But everybody's looking forward to it because they're going to have picked a really spectacular object. So everybody is really looking forward to that first image. I say the science that will come from it is going to be really, really exciting. But it's not just the James Webb. There are plenty of other exciting telescopes on the horizon as well. One of those is the Vera C. Rubin Observatory. Now, this is a ground-based observatory. This is a big telescope on a mountain in Chile. And this telescope is exciting for different reasons to the James Webb Space Telescope. It's a very different kind of telescope. So it's going to work in the visible part of the spectrum, so the kind of part of the spectrum that we're all used to using with telescopes. It's got a very long focal length, a very fast focal ratio. This is a very fast telescope. It's very big, so it's very sensitive, but it's also very fast. And that means it's an excellent survey instrument. And the aim of this telescope is to basically map the sky very rapidly, looking for things that change. It's a transient machine, basically. So what it's going to do is it's going to observe the sky. It's got a 3.2 gigapixel camera with a field of view that's about, it's 3.5 degrees. So again, several times the width of the full moon. And it's able to take an image down to a really good sensitivity in just 15 seconds. So with that short exposure time, it's going to be able to map basically most of the sky that it can see from its location on the mountaintop in Chile every night. And because that is going to result in a vast amount of data, we're talking more than a petabyte of data per year, a lot of the processing, a lot of the searching for those transients is going to be done not by human beings, because there aren't enough graduate students to actually go through all of those images in detail and find those things that change. It's going to be done by computers. It's going to be done by algorithms that will compare, okay, what does the sky look, that patch of sky look like tonight? What did it look like last night? We'll compare those images and look for things that have changed. When things change, it will send a message to an astronomer who will then go and make an assessment as to whether that's something that's interesting and worth following up, or whether it's just a satellite, or it's, you know, it's something we already knew about. Now it's an asteroid. We know it's there. It's fine. We can ignore that one. So, like I say, it's going to be, if it's taking an image every 15 to 20 seconds for a whole night, and it's going to be doing that every night of the year that's clear, that's an awful lot of images and an awful lot of data. So again, this is something that's going to keep astronomers busy for a very long time. The transient science is going to be phenomenal, but as you do that observing, as you go through, you take those images night after night after night, you build up a very deep image of every patch of sky. You can stack all of those images that you take over time. You end up with really deep images of the sky as well. So the archive of data this telescope will produce will be something that, as I say, will keep astronomers busy doing all kinds of astronomy, all kinds of science for many years to come. And the kind of things it's going to do, it's going to help us study things like populations of supernovae. We know there are different types of supernovae, ones that are formed by massive stars when they reach the end of their lives and collapse in the core collapse process and then explode violently. And then there are others where you have thermonuclear supernovae, where you have white dwarfs that accrete material, they go past a certain mass limit and they explode catastrophically as well. So we know there are two main classes of supernovae, but we know there are lots of subtypes as well. One of the things that astronomers really enjoy doing is looking at statistics. We can learn a lot about populations. We can learn a lot about the physics by looking at the statistics of populations. But to do that, we need large populations. We need large numbers of objects to study. And the Vera C. Rubin Observatory is going to give us vast numbers of these transient objects, of these supernovae, to help us with those statistical studies. It's also going to help us look at the type 1a supernovae. These are the ones that are the thermonuclear in nature, and we think they have the same brightness, which means you can use them as standard candles. You can use them to measure the expansion of the universe. And these are the kind of supernovae that we used some years ago now to determine that we think the universe is actually accelerating, that expansion is accelerating. And that's something that's still being actively studied. So again, a large population of those type of supernovae will actually help us with our studies and our understanding of the expansion of the universe, because there are still unanswered questions in that field. Again, it will also help us map those smaller objects in the solar system. And because it's observing the same patch of sky repeatedly, it will help us map their trajectories to a high degree of accuracy. We'll be able to know not only where these objects are, but where they're moving and where they're likely to be in the future. We'll be able to get very good sets of orbital elements for them. It will also potentially help us discover other types of transient objects that so far we don't know are there. One of the things that happens every time you build a telescope that has new capabilities, opens up a new area of parameter space, you end up making discoveries that you didn't know were there to be predicted in the first place. And that's one of the hopes of the Vera C. Rubin, is that actually it helps us discover transients, so short transients that sort of appear and then disappear on shorter timescales than we're used to with novae and supernovae and so on. that maybe we just haven't seen before because we haven't had this kind of observing capability before. So it's definitely a telescope to watch. And I believe that a lot of the alerts that it produces will be made publicly available. So if you want to go, if you're interested in transient objects, if you're interested in supernovae and novae and variable stars, and you want to get the data from Vera C. Rubin, I believe you will be able to get hold of that information. So you can do your own follow-up and possibly contribute to some science as well. There'll be a lot of scope for doing follow-up observations, and the amateur community will be very, very welcome to get involved with those efforts. So we've looked at the James Webb Space Telescope in the infrared. We looked at the Vera C. Rubin in the optical, because I'm a radio astronomer, so I can't not tell you about a radio telescope. So because the biggest radio telescope on the horizon is the Square Kilometre Array. This is a telescope that's so big and so complicated that it's actually involving more than one type of antenna, several different receivers, and in fact, more than one continent. This is an artist's impression of what some of the antennas are going to look like. The original image that came from the SKA office, the Square Kilometre Array, actually had an optical picture of the Milky Way in the background, which I thought was a bit daft because that's not what the Square Kilometre Array is going to see. So I photoshopped out the optical image and photoshopped in a picture of the radio sky. This is what the Milky Way looks like in the radio regime. So this is what you would see if you had radio eyes and you look towards the galactic center. This is what you would be seeing. So down here somewhere is Sagittarius A star, where our supermassive black hole is. And you can see there's a lot of interesting radio structures in there. And one of the reasons for showing you this is to show you what radio astronomy can do. We talked a little bit before about how radio telescopes can see through clouds. Luckily for the likes of me in northwest England, where it rains a lot, we have a big radio telescope and it can see through the clouds. It doesn't matter if it's raining. Radio telescopes can also see through the dust and gas that permeates the universe and is really thick in the plane of the Milky Way galaxy itself. If you remember back to the Gaia map I showed you of the Milky Way, even the dust lanes are visible in the Gaia map. There's a lot of obscuration there. There's a lot we can't see in the center of the galaxy using optical telescopes or even infrared telescopes. The best way to see what's going on in the centers of galaxies behind all of that gas and dust is to look with radio telescopes, where most of that gas and dust is completely transparent. So what will the Square Kilometre Array do for us? Well, it's going to, a lot of the same kinds of studies that things like the James Webb Space Telescope is going to let us do, but looking in a different part of the spectrum, which gives us a different window on the physics of what's going on. So it's going to help us look at galaxy evolution. As I say, with radio waves, we can see into the dust and gas that permeates galaxies. And one of my areas of interest is looking at starburst galaxies, those galaxies where often there's an interaction between two galaxies. That interaction causes the gas clouds to collide with each other. That produces a lot of star formation, which produces a lot of supernovae, which results in a lot of dust, which results in a lot of obscuration. So studying starburst galaxies in the optical is very difficult because there's so much of this dust there obscuring what's going on in the centers of these galaxies. In the radio, we can see through all that. We can look at these processes going on in the middle of these galaxies, and that can let you measure the supernovae, which can tell you about the star formation rate, how fast the stars are forming in that galaxy. It can also let you look down towards the central supermassive black hole. So in this case, in the Milky Way, we've got Sagittarius A star in the center, but every galaxy has a supermassive black hole in the center, and some of them are far more active than the one in the center of our galaxy. And that activity is something that, again, you can probe with radio telescopes. So that's something that the SKA will help us do in more detail. It's also going to help us look again at those very early galaxies in the very early universe. So looking back nearly 13 billion years towards the Big Bang and seeing the first stars and galaxies and hopefully the first evidence of black holes in the early universe. We know that every galaxy has a supermassive black hole in the center. What we don't know is whether those black holes formed first and the galaxies formed around them, or whether galaxies formed out of the gas that was in the early universe and the black holes formed in the center of those galaxies. We don't know which of those is the case. And that's something that the Square Kilometre Array will hopefully allow us to shed some light on. It will also help us do strong field tests of gravity. So the kind of experiments testing Einstein's theory of general relativity that we just cannot do on the Earth's surface in a laboratory because we don't have the right physical conditions. Using radio waves, we can study things like pulsars, dense neutron stars with very strong gravitational fields, black holes with even stronger gravitational fields. And we can watch things fall into those objects and see how they behave and test to a really high degree of accuracy Einstein's general theory of relativity. Again, experiments we just cannot do on the Earth. We can use space as our laboratory to do these tests. It's also going to let us actually do experiments related to the SETI project, the Search for Extraterrestrial Intelligence. One of the things that the project is actually going to do, as the observations for science are being undertaken, the data will be capable of being taken and sent to another computer for processing in a different way. And one of those pipelines will be to take data out to look for signals that may be of extraterrestrial origin, so not created by stars, planets, galaxies, colliding black holes, whatever. Look for the kind of signals that could only be generated by something with an intelligence behind it. The chances of finding it are fairly small, given the size of the universe and the number of life forms that we currently know in existence outside of the Earth is 0. But if we don't look, then the chance of finding it is 0. And as we can do this without impacting operations on the telescope and without impacting on the actual science operations, it's a very, very sensible thing to do. So that's an overview of some of the telescopes, again, that I personally think are the most exciting ones on the horizon, the most exciting ones I think are worth watching in the next few years. But of course, it's not all excitement and wonder and amazing things. There are challenges on the horizon as well, and there are some quite significant challenges. And probably the biggest challenge that we have in the near future is the problem of satellite mitigation. I don't know how many of you have actually seen Starlink satellites in the sky. I know a lot of my astronomer friends have been out and have watched them go across the sky. And at first, when they first launched, everybody's like, wow, that's pretty. And then people started going, hang on, how many are they wanting to launch? It suddenly dawned on the astronomy community that, hey, no, this is actually going to be something of a problem. So this is an image from Chile of these satellites passing over the Cerro Tololo Observatory. And it's going to be a huge problem for any professional observatory. But if you imagine the Vera C. Rubin Observatory with its 3.5-degree field of view, that's quite a lot of sky. If you've got hundreds of thousands of satellites in orbit, every single image is going to be affected by satellites. This is an example of what's been happening already. This image is already a couple of years old now. And this was when there were only a few sets of Starlink satellites in space. But this is DCAM. This is again a telescope that has a large field of view. Each of these rectangles is a different CCD at the focal plane of the telescope. So this is showing you just how much of this is affected even in the early stages of the satellite deployment. And you can see even here most of these CCD chips are affected by this particular train of satellites. There's hardly any of these images that aren't affected. I think this one escaped, but there's not many that escaped these satellites altogether. And this is a problem for something like DCAM, because DCAM is doing a detailed, highly sensitive survey of the sky to look for very, very subtle effects in the morphologies of galaxies. And if you have satellite trails affecting your images, again, your data are useless. You can't subtract them, you can't get rid of them from the data because they're so much brighter than the information that you're trying to do the science on. So this is going to be something of a headache. Now, of course, it's not just SpaceX. There are plenty of other satellite companies they're planning to do stuff. So this is a video that was put together by AGI.com. You can find this on YouTube, and the commentary that goes with it is really quite interesting. But again, so this is going back to, this was made in 2017, but it shows you the scale of the problem. Each of the sets of dots in here is a different set of satellites that are, well, at the time this was produced, they were already in the planning stages. So these were requests to launch that had already been submitted to the relevant authorities. And you can see the numbers are going up, if you'll pardon the pun, astronomically. This problem is going to get much, much, much worse. And you can see there are certain parts of the Earth's surface here where you've got many more than others. You know, even at the poles, you don't escape these satellites, but there's basically nowhere on the Earth's surface that escapes these satellites. They're going to affect our view of the sky as people just going out and having a look, but it is going to be a major headache for pretty much every professional telescope. Now, there are very good reasons for having satellites in space. We've already, you know, a lot of our banking, a lot of our infrastructure already depends on satellite communication. And for disaster response, the likes of the recent volcanic eruption in Tonga, a lot of the satellite observations of that are being instrumental in the relief efforts and the help that's going to be needed on the ground there. We can see what's needed, we can see where the help is needed, and we can go and we can make that assessment when local connections are down. So having satellites in space is a very good thing. And in fact, there are some very good reasons for having an awful lot of satellites in space. And there is even an effort to use space technology, to use satellites, to use these constellations for advancing the Sustainable Development Goals, the UN Sustainable Development Goals. And in fact, using satellite technology can help address all of these Sustainable Development Goals to make the world, you know, a better place for everybody, which is a very good thing. But one of the big questions that isn't really being talked about, but is becoming more of an issue, is there actually space in space for all of these satellites that people want to put up there? This is a graph that I put together taking data from the UN Office for Outer Space Affairs, and they track launches across time. So what they've got here in the bars show you the number of launches per year going all the way back to 1957 and the launch of Sputnik. And then we go up to the 2020s, and you can see the numbers of satellites have been shooting up dramatically. The blue line here is this cumulative launches. So you can see that for most of our spacefaring time as a species, the number has been going up at a fairly steady rate. And now we're into this massive rise in the number of satellites being launched. So in 2020, we launched double the number of satellites in any previous year. And again, in 2021, again, the numbers went up dramatically. In 2020, we didn't double them, but it was still a significant increase. And I think by the end of last year, it was over 1,800 satellites had gone up just last year alone. So according to the UN Office for Outer Space Affairs, there are currently over 8,000 satellites in Earth orbit. Now, a lot of those are not actually operational. A lot of those are defunct satellites, things that have come to reach the end of their operational lifetime, or they've failed. And some of them are actually spent rocket parts that were used to launch something else. They went into orbit and they're still up there, still orbiting. And in fact, there are over, according to the NASA office that track these things, there are over 23,500 objects greater than 10 centimeters in size in low Earth orbit currently. That is a huge number, and it's a big risk. And as I say, there are plenty of other companies that want to launch satellites, and the most stunning one I saw recently was this from Jonathan McDowell, who tweeted that Rwanda has filed with the International Telecommunications Union a proposal to launch 327,000 satellites. This is thoroughly unrealistic, according to a lot of observers. Noting, of course, that Rwanda does not currently have a satellite industry. So what's behind this application? At the moment, we don't know. Whether it will actually happen or not, again, we don't know. But there are a lot of these sorts of plans being proposed at the moment. And of course, the risk is if you put too much stuff in low Earth orbit, if there's too many things in orbit close to each other, of course, we might end up with this sort of scenario. If you've seen the film Gravity, this will be very familiar. This is a screenshot from an image from a still from the movie Gravity. Of course, the concept of that movie is that there is a collision between two satellites. And when they collide at kilometers per second. They're moving very fast relative to each other. Those collisions have a lot of energy. The satellites disintegrate and send many bits of debris flying out in all directions. If you're unlucky, one of those bits of debris can hit another satellite, causing another catastrophic destruction, which can go on and trigger another catastrophic destruction, and that process can snowball until you end up with basically one giant layer of debris surrounding the Earth. This is something called Kessler Syndrome. It was first modeled back in, I think, the 1950s. And this is a very real risk, because this was a fictional scenario, but the real risks are definitely there. This is, as I say, getting worse and worse. This is, again, a few years old now. This goes back to 2018, but it shows you the number of operational satellites follows this line. So at this time, at the end of the graph, there were 1,700 operational satellites. The pink line here shows you the fragmentation debris. So this is just bits that were created when there were collisions or when rocket launches happened and bits fell off and so on. And this is the total number of objects. And you can see here, there was a dramatic increase in the number of objects in orbit. Again, it's fragmentation debris when there was a deliberate destruction of a Chinese satellite. And then we had an accidental collision between a Cosmos and an Iridium satellite back here in 2009. And again, dramatically increased the number of bits in low Earth orbit. In more recent times, just at the end of last year, we actually had an accidental collision. Right, yes, what was I saying? Yes, in December this year, we had a collision between a Chinese meteorological satellite with debris from a rocket that was actually launched back in 1996 and was still in low Earth orbit. And that collision, again, produced a vast amount of debris, just adding to the problem. And that was a completely accidental collision. Nobody predicted it was going to happen. But things that also don't help are, again, at the end of last year in November, we had a deliberate Russian anti-satellite test where they deliberately blew up one of their own satellites. Again, this kind of behavior in space is something that's just going to be less and less acceptable as more and more of our infrastructure, more and more of our communications come to rely on satellites. And the Russian satellite test was particularly destructive because the orbit that the satellite was in, the debris, 1,500 pieces of it, was a direct threat to the International Space Station and to the lives of the astronauts on board. And of course, last year there was also the memo from the Chinese authorities to the UN about the close encounter of 2 Starlink satellites with the Chinese space station. So this is, at the moment, there is nothing in the way of legislation or international law that regulates a lot of this stuff. So these are things that governments are going to have to come together and discuss in detail, and there are going to have to be discussions at the UN trying to come up with ways that we actually regulate the use of low Earth orbit to try and avoid this sort of thing happening. So with satellites affecting our view from the ground, and low Earth orbit can becoming a fairly dangerous place to put a telescope, should we be looking around for other options over, looking forward to the next 200 years? Now, I would argue, yes, we should absolutely be looking for other solutions. And in fact, some time ago, I wrote a tongue-in-cheek post. I made a tongue-in-cheek graphic about the idea of putting something like Arecibo, the Arecibo radio telescope, on the moon. So this is Arecibo photoshopped into a crater on the moon. The advantages of this, you don't have the atmosphere to contend with because the moon doesn't have any atmosphere. You've got a low gravity environment, so you can build bigger structures than you can on the Earth, and you don't have the same stresses due to gravity, and you don't have the same stresses due to wind either. But the disadvantage is, of course, maintenance is hard. It's expensive to send astronauts there to go and fix something if it breaks. So you want low maintenance telescopes if you're going to put them on the moon, which is why Arecibo would be a sensible thing to put up there, because Arecibo, big dish that sits in the ground, the only bits that move are on the receiver cabin. Of course, Arecibo sadly is no more, but that doesn't take away from the fact that it was comparatively a low maintenance telescope and something that would be ideal for operations on the moon. And in fact, again, something that was affected by COVID, but there was actually a meeting planned at the Royal Society in March 2020, just as we went into our first lockdown in the UK. Due to COVID, there was a meeting that was to look at astronomy from the moon. How do we do this? What should we be looking at? What kind of science can we do from the moon? What would it be beneficial for us to do there? It would be very advantageous, for example, for infrared telescopes. Again, it's a cool environment. Some in the permanently shadowed craters at the poles would actually be a very, very good place to put an infrared telescope as well. So it has advantages for optical, radio, and infrared astronomy. The meeting didn't go ahead, it's been postponed, but they did put together a special edition of the proceedings of the Royal Society. So if you want to look at the discussions that would have happened at the meeting, then you can go and have a look at this publication. All of the discussions are there instead. We've also had other meetings recently about how we deal with protecting the night sky for astronomy, but not just for astronomers, for the public as well. Looking at the sky is something that humans have done ever since there have been humans. Looking at the sky, wondering what we're seeing up there. What does it all mean? What does it mean for us? Does it tell us about who we are, where we came from? And today, most people live in cities. Most people can't see the Milky Way anymore. An awful lot of people. I grew up in Manchester. From Manchester, you're lucky if you can see the Moon, Venus, Jupiter, Sirius. You can't really see much else most nights of the year unless you're very, very, very lucky. And that reality is the same for an awful lot of people. So there was a meeting in 2020, again, online because of COVID, that looked at protecting the skies. And there were several working groups that were formed, and they went off and put together detailed studies of how we deal with light pollution, how we deal with radio pollution, how we deal with radio interference, how we deal with protecting the skies, creating reserves with dark skies for the public to go and experience those dark skies and see the universe in all its glories. The final documents for that were presented to the UN, and we actually had a follow-up meeting a year later. This one was planned to be a hybrid meeting on La Palma, but just before this meeting was due to take place, the volcano on La Palma erupted, and again the meeting had to be moved back to being fully online, sadly. That volcano, I think, is still erupting on La Palma several months later. Again, it's caused quite a lot of destruction on the island, very sadly. But again, if you want to read the publications that came out of this meeting, again, this was looking at the results from a lot of those working groups on presenting, how we can go about protecting the skies for the various different, optical, infrared, radio, and looking at the problem of satellite mitigation as well. Then again, you can see the results and recommendations in the link that I pasted at the bottom there. So that's what astronomers are currently doing to try and solve some of those big problems that we've talked about. Looking a little bit further into the future and past the telescopes that we've currently got on the horizon, the ones that we know are coming online. Telescopes on the moon is one thing, but maybe we should be looking a bit further afield. Maybe we should be looking at putting telescopes further away in deep space. James Webb Space Telescope is going to L2, which is a distance 150 million kilometers from the Earth. Much, much cooler and darker, further away from the Earth than most telescopes go. But we can go further still, and arguably for radio astronomy, we want those high resolution images. To get the high resolution images, we need to separate our telescopes. The further apart you put your radio telescopes, the better resolution your array has. And at the moment, the best we can do is the diameter of the Earth plus a satellite in an elliptical orbit around the Earth. That gives us a telescope effectively twice the diameter of planet Earth. If we can put an array of telescopes out in space, then we can make a telescope as big as we like, essentially, and that gives us much, much better resolution and hence much more detailed images of the radio universe. So this image, again, is slightly fanciful. This is an image from Star Trek. This is the Argus array, which is a subspace telescope. Now, subspace waves travel faster than light. So technically, the Argus array would let you observe things before they happened, which is physically not possible. But it's Star Trek. It's a bit of fun. Suspend your disbelief. We are actually putting a lot of telescopes in space. So we have already the James Webb Space Telescope. We have other telescopes in Earth orbit, but we are planning to put telescopes further afield as well. And one of the reasons we want to do that is to look at gravitational waves. I mentioned these briefly at the beginning. This is our other window on the universe, something that's outside the electromagnetic spectrum. Is completely separate to what we're used to looking at the universe. So it's completely different to X-rays, gamma rays, radio waves, infrared, ultraviolet, optical. This is a very, very different window on what's going on in the universe. And we get these gravitational waves when massive objects spiral towards each other and collide. The ripples from that collision spread out through the universe, actually altering the fabric of space-time as they do so. And those gravitational wave detectors, basically large cavities with lasers passing between mirrors, can detect these very, very subtle changes in space-time over large distances. Now, the longer your cavity is, the further your lasers travel, the longer the wavelengths of those gravitational waves that you can detect. So at the moment, the gravitational wave detectors that we have are very good at detecting collisions of neutron stars, so collapsed cores of massive stars, and small black holes, stellar mass black holes, again formed from supernovae. If we want to study supermassive black holes colliding, we think, as I say, every galaxy has a supermassive black hole in the center. We know a lot of galaxies collide in the universe. We see a lot of them in various stages of that collision process. In the early universe, we think that process happened a lot more frequently. To study that, what we need to do is detect those black holes actually colliding with each other. And the way we can do that is using long wavelength gravitational waves. But to do that, we need very, very long cavities for our lasers, actually longer than the size of planet Earth. We actually can't do some of this observation from the ground itself. So to see that part of the gravitational wave spectrum, we have to go to space. And there is a project, there is a plan to put a laser interferometer in space. It's called LISA. And it's 3 satellites in a triangular configuration. LISA flying around in space again. Okay, so yes, this is a project that's actually got quite an advanced stage now. The test satellite has been launched. It worked. It actually worked much better than the specifications. To do these kind of observations, you need very, very good accuracy in your measurements to measure these very subtle effects in the space-time fabric. So this project is one that's definitely worth watching when they eventually get to the point where they can launch the full set of satellites. Again, whole new window on the universe. And as I said with the Vera C. Rubin Observatory, when you open up a new capability that you haven't had before, chances are you'll make discoveries that you didn't know were there to be predicted. So this is definitely something to keep an eye on. So again, slightly more longer term predictions. Again, this one's a fairly easy prediction to make. We already talked a little bit again at the beginning about how the numbers of exoplanets that we know of have gone up dramatically since the 1990s when we first started discovering planets around other stars. It's unimaginable that we will stop finding exoplanets because there are lots of projects on the go to do this, and it's something that the Vera C. Rubin will help us do because it will be able to monitor the brightnesses of stars and will actually help us find planets by the transient method. But there are plenty of other observatories planning to do this sort of thing as well. So again, I'm going to play this little video again. This video takes us through from the 1700s year by year and shows you how many planets that we know about, and it plots their period against their masses in Earth masses. This graphic was put together by Hugh Osborne, who was a PhD student at the time, and he was very disappointed to find this was his most cited piece of work. None of the research he actually did for his PhD, but this graphic he put together in his spare time for a bit of fun has got far more coverage than any of the actual research he's been doing. But it's a really nice illustration of just how fast we've been finding exoplanets in the last few years. And this graphic at the top presents the same information just in graphical form rather than in an animation. And you can see the trajectory here again is going up rapidly. And if you extrapolate that trend line in a very unscientific way, of course, because there's a huge uncertainty in there, and we don't know what projects are going to be around, and we don't know if we can keep discovering them at the same rate. But if you extrapolate that trend, then in 200 years, by 2022, we will have discovered over 21 million exoplanets. Now, of course, that's nonsense. We won't have that many exoplanets by then, but that just shows you the rate of increase at the moment. If we could sustain that set of observations, then it would just be phenomenal how many of them we would find. So the number is clearly nonsense, but we will definitely find many, many more of these things. The more we look at our nearby part of the Milky Way, the more of these exoplanets we find. And it looks like the vast majority of stars have planets around them. So we will be finding lots more of these things. And as you can see from this diagram, there's quite a variety of parameters of these planets as well. The early exoplanets we were finding were the easy ones. They were the gas giants orbiting close to their host stars because those are the easiest ones for these techniques to discover. As our techniques have got more refined, as our telescopes have got better, we've started to find smaller planets orbiting further away from their parent stars. We've started to find Earth-like planets in the habitable zone of their parent stars. And those, of course, are the next candidates to go and look for signatures of life. And there's a lot of work going on at the moment, looking at the ways to take the spectra of the atmospheres of these planets to look for signatures of, again, the chemicals associated with life, in the same way that the trace gas orbiter of ExoMars is looking at the atmosphere of Mars. There are people actively trying to do the same thing with exoplanets as well. Very, very challenging observations, but very, very worthwhile if they find anything. Now, of course, when I first wrote this talk at the end of 2019, beginning of 2020, the topic of conversation amongst most astronomers I know anyway, was, is Betelgeuse about to explode? Now, of course, Betelgeuse has gone back to its old self now since then, but at the time, it had dimmed by more than a magnitude. And this got a lot of people very, very excited, because Betelgeuse is a supermassive star. It's a massive red giant. And it is one of those stars that will go supernova at some point. It's 11 times the mass of the sun. So when it goes supernova, it's going to go bang, and it will be very, very bright. And because it's relatively close, of course, this will be extremely bright to us on the Earth. It will be bright enough, we'll more than likely be able to see it in daylight. So of course, again, in a very unscientific way, I had a bit of a play around with Photoshop. Betelgeuse goes bang. We get a very, very bright supernova. It fades away, and what we eventually end up with is an expanding shell of basically the shockwave expanding after the explosion as a supernova remnant. Now, it will never really be this big and this bright on the sky. This is a little bit of artistic license. If I'd done it to scale, you wouldn't see it. It would be less than a pixel. But this is an artist's impression of what the supernova remnant might look like. Now, we know it is going to go supernova. That dimming turned out not to be a precursor of the supernova explosion, of course, because Betelgeuse is still there, or at least it was when I saw it a few hours ago here in the UK. It'll probably be quite high in your sky by now, but yeah, here I'm pretty sure it's set by now. So of course it's not gone supernova yet, but that doesn't mean it won't in the near future. So every night I see Orion, I do go like, no, it's still there. It's not exploded yet. We don't know when it will happen. It could be tomorrow. It could be in 600 years. It could be in 6,000 years. We just don't know. We don't have the understanding of stars to do that kind of observation at the moment. But if you're interested in following what it is doing, then there is a Twitter account, Beetlebot, that takes observations from the AAVSO and plots them on a regular basis. And currently, when I checked earlier today, it was 86% of its usual brightness. So you can see the dimming here 300 days ago, and then it's gone back up. So this is when it's too close to the sun to do observations. It's gone back up. So it is a variable star. It goes through these variations anyway. The particular dimming back in 2019, end of 2019, beginning of 2020, appeared to be due to dust. And again, this is something that massive stars do. They do produce a lot of dust. So they do occasionally go through these periods of unusual dimming. So on this occasion, it wasn't a precursor to the supernova explosion, but keep your eye on it, because at some point it is going to explode. So another thing looking forwards then, of course, this is looking slightly more than 200 years into the future now. Again, this goes back to the Gaia results, the Gaia data release 3. So there's 1.8 billion stars. Now, it gives us accurate positions of these stars over multiple epochs. And what that lets you do is map the motions of these stars on the sky. And again, that helps us understand our own Milky Way galaxy. But what it means for us on the Earth, of course, is that all the stars are going to move on the sky. So the constellations that we know and love today, of course, will look very, very different. Now, of course, in timescales of 200 years, they're not going to move. Most of them are not going to move appreciably. So the vast majority of people would not even notice. But the simulation here, this is projecting the motions as measured by Gaia out for the closest 40,000 stars close to the Earth. So not all of the stars in the catalogue, because then it would just be a big blur of white, but just the nearest 40,000 stars. So those within 100 parsecs of the Earth, and projecting them forward not 200 years, but 400,000 years. So you can see some of these stars are moving very, very fast and are going to zoom across the sky on those sorts of timescales, because in 200 years, because we won't notice them. But the universe is always in motion, of course. Now, the safest prediction I could possibly make is that we will discover the unknown unknowns. There those things that we don't yet know are there to be discovered. And I've alluded to this a couple of times, that every time we get new capabilities in our telescopes, we build telescopes to do particular science observations. So we built the James Webb Space Telescope to look at the first stars and galaxies, to help us understand star and planet formation. But it will also uncover things that we don't yet know are there to be predicted, because we've never had that capability in the infrared before. The same with the Hubble Space Telescope. Hubble showed us lots of things that we didn't know were there when we were planning the Hubble Space Telescope. The same in the radio, when people were planning the Lovell Telescope, the 76-meter radio telescope at Jodrell Bank in Cheshire, where I did my studies. They didn't know that quasars existed. We didn't know that pulsars existed. And those are some of the things that the telescope now spends most of its time doing. So every step forward in observational capabilities leads to new discoveries that could not have been predicted before we built that telescope. So deeper observations always reveal new things. Faster observations always reveal new things. And with today's new capabilities, where we've got multi-wavelength coverage going across the entire electromagnetic spectrum, all the way from gamma rays to radio waves, but also that multi-messenger capability that we now have with gravitational waves as well, giving us a whole new window on that physics, plus the time domain, that rapid observations, the kind of thing that the Vera C. Rubin Observatory is going to give us. These are all developing, and they all complement each other, and they all help, they all combine to give us a really good view on the universe. So going forward over the next 200 years, my hope is that we will keep that multi-wavelength and multi-messenger coverage of the sky that we currently have, and that those cheap launches that I mentioned earlier make this a real possibility, that we are able to keep that coverage that we have today, and that allows us to keep making these discoveries for the next 200 years. Now, my final prediction, if my computer will let me without crashing again, was that in 200 years, we would all, again, bear in mind when I wrote this talk at the very beginning of 2020, my final prediction was that in 200 years, we would all be meeting by hologram. And then, of course, 3 months after I first gave this talk, COVID hit, and we all got very, very familiar with Zoom, Teams, etc. So this prediction came true a little bit sooner than I'd anticipated. But with any luck, going forward after COVID, hopefully, my hope is that we'll be able to do more meetings like this, more meetings in hybrid mode. Better for the environment, it's better for people's sanity. I don't know about you, but I don't miss commuting to work. I'm very glad that after COVID, I will be able to do some of my work from home on a more regular basis, and that I won't have to travel around the world to go to conferences a couple of times a year, because some of that I could really do without. So I hope that we'll learn something from the terrible experiences that we've had, and hopefully some things are better as a result of it. But with that, I will bring it to a close. Those are, as I said at the beginning, these are some of my predictions, some of my hopes, and the telescopes that I think are particularly interesting that are going to come over the next few years, and making some slightly more whimsical predictions for the next 200 years. But thank you very much for your attention. Thank you very much for your patience with my computer. And yes, it's been a pleasure. Thank you.
Thank you very much.
Yeah, thank
Thank
you.
Thank
The
you.
pleasure has been ours to listen to such a wonderful program, Laura. I mean, not Laura.
Yeah,
I mean, Megan, I got your name wrong. That's embarrassing.
yeah.
I claim the
Everybody-
senior moment. Thank you so much.
I got a question. When do you?
Yeah, go.
When do you think that we're gonna like map exoplanets? You know, like not just know they're there, but you know, take a picture of them, sort of like you have a satellite around Earth that can map the Earth, and then we'll actually have an idea of like, oh yeah, Sirius has got 4 main planets and 3 gas giants, and you know, maybe we'll even find an exoplanet with signs of civilization. But you know, when do you think that could happen? You know?
Well, as I say, there's a lot of a lot of observations happening, right? So there's this big effort to look at the spectroscopy, to look at the details of the atmospheres of some of these planets. And I can't stress enough just how challenging an observation that actually is.
Yeah.
You've got to get past the brightness of the host star, which is many, many, many times brighter than the planet itself, by many magnitudes, so hundreds of times brighter in terms of absolute luminosity. And spectroscopy is hard enough anyway. So this is a real observational challenge. But they're making progress all the time. So I hope that we'll start to see results on that in the next few years, is my prediction. In terms of imaging, again, it's a huge challenge, and partly because of that contrast issue, right? You've got that massive star with a huge amount of brightness. Even if you're looking at a red dwarf, it's still much brighter than the reflected light you're getting from the planets. Again, there are sophisticated techniques, so you can use coronagraphs to block out the light coming from the star and take an image of the planet. But again, we don't have the resolution to see anything other than essentially an unresolved blob. So my feeling is that I think the most interesting results we will get will come from that spectroscopy, because with the spectroscopy, you don't need to be able to resolve them in an imaging sense. You can do it on a single pixel. So if you can get that spectroscopy right, you can get that technique sorted out, that will give us the best understanding of what's going on in some of these exoplanets.
Megan, I got 2 questions if you have time.
Go for it.
Okay, so the first one is non-technical, and I'm wondering, are astronomers, professional astronomers, concerned at all with the political climate where a lot of these super giant telescopes exist? For example, like, in Chile, I don't know how many are in Chile, but it seems like it's got to be a massive number of wonderful telescopes there. I often wonder, well, Chile's been pretty neutral, it's been pretty safe, but do astronomers ever worry about the political climate where these scopes are put, and then having access to them in the future when you need them?
Yeah, it's a good point. I have to say, I think it depends where the telescopes are, okay, because some countries are historically more stable than others. So yes, most of the big telescopes are also built through cooperative agreement between countries, or at least between research organizations and universities, because most of these telescopes being built now, essentially, again, it comes back to the issue of we've done the easy stuff, right? In astronomy, we've picked out all of the stuff you can do with a 2-meter size telescope. So the interesting science now is you need a bigger facility to do it, and that makes it much more expensive, which means that a lot of these things have to be done by big collaborations, because there's just no other way to get it funded. And yes, people do think very carefully about where they site their telescopes, not only for science reasons, but for political reasons as well. Although sometimes the politics can actually make that harder. Sometimes telescopes get put in places that are politically advantageous to the detriment of the science. So it works both ways. There are other issues as well that, again, astronomy historically has not been very good at dealing with. So I don't know if you're aware of the issues on Hawaii with the sighting of large telescopes in Hawaii, and the controversy with the indigenous population there. In some cases, astronomy handles that really badly, and that's the case where astronomy has got it wrong. But there are other cases where astronomy has got it much better, and that one of those examples is with the Square Kilometre Array in Australia, and I have first-hand experience of this. The picture on the wall behind me, this is actually a piece of Aboriginal artwork from a field trip I did to the site, for the Australian site for the Square Kilometre Array, with a group of Aboriginal artists and local tribal leaders. And there was a big effort there before anything was put on the ground to talk to the local population and get them involved as part of the process, so that they felt like they had some ownership over what was going on. It's their land, they own the land. So there were agreements negotiated to use the land in the first place from the beginning of the project. So I think astronomy as a globally has learnt from where this has gone wrong in the past, and we are now doing things like that much better than we did. But yeah, you're right, the politics is difficult, and I think it's always going to be difficult, and there is always that risk. You put a telescope somewhere because it's got good dark skies, you are not guaranteed that you will always have access to it, because who knows what the political situation might be in 10, 15, 20 years time.
Yeah, okay, thank you. And then the second question, the graphic that you had showing the number of satellites orbiting was striking. I mean, it's actually shocking. And I'm wondering at this point, are the number of satellites up there, are they already creating problems for professional astronomers? I mean, it is already a problem for them.
Yeah, it is. It's already a problem, certainly for optical telescopes. So I showed you the picture from the DCAM with all the individual CCD frames. That's already affecting them. They're getting to the point where they're struggling to operate. They now can't do anything within so many hours of twilight because there's just too many satellites. That's where they see the worst reflections. So they're having to restrict their operations.
It seems like the moon is, the only place is really a good idea because it's close enough that they can be serviced and built. And, the thing with Webb, what worried me was I'm all for a Webb, don't get me wrong, but you get one shot at getting it right. And if something goes wrong, it's so far out there that it's non-serviceable. And look what happened to Hubble. And look at how many service missions we've had with Hubble. We haven't got that option with Webb. So it's like, what, $10 billion for Webb? That's a lot of eggs in one basket.
Yeah, it is. My favorite number with the Webb was, it cost $10 billion. And I spoke to a journalist from a national newspaper here in the UK just before Christmas. And he said, what can we really justify spending that much money on a spacecraft, on a telescope in space? And I went, well, look at it this way. We're trying to understand the entire history of the universe here. That's 13.7 billion years ago. That's less than $1 per light year. I don't know about you, but I think that sounds like a pretty good deal. So if anybody ever says, why are we spending this money? That's one to remember. The moon is a good place to put, as I say, some kinds of telescopes. So yes, it's good for infrared, it's good for optical, and it's good for radio. But yes, you want simple telescopes that don't need as much maintenance and stuff that can cope with the dust, because there's a huge amount of dust on the moon. So you have other challenges to cope with there. Servicing, yes, is easier than servicing the James Webb, but it's still expensive compared to having a telescope on a mountain in Chile or Hawaii or the Canary Islands or whatever. But the problem with putting telescopes on the moon is that you're not really safe there from satellites, because there is already talk of putting a network of satellites around the moon so that you've got communications when you're on the far side. The same on Mars, for when astronauts go to Mars. So realistically, you're not safe there either, not in the longer term. It's fine for now, but it won't be long before these kind of networks are there as well. And as I say, it's not just a problem for optical, it's a huge problem for the radio. So at the moment, radio telescopes, we've seen a massive increase in the amount of interference we see on our radio data. As I'm sure anyone here who's a radio amateur will also have suffered the same thing with radio receivers, right? The sheer number of gadgets people have now, and the sheer number of them that actually have really poor ANC characteristics, it means that you've got a lot of interference. If you have something like the Hubble telescope, where I studied, 76 meters of diameter, that's a pretty big, pretty sensitive telescope. And it's actually sensitive enough, it can pick up a single mobile phone on Mars. I know because we've tried. The Beagle 2 was a British probe that went to Mars. Sadly, it failed. But we at the observatory put a special receiver on the telescope, and we spent several days listening for the signals coming from that transmitter, which were about the strength of a modern mobile phone. So you can imagine if your telescope is that sensitive, then a mobile phone, in the next village, 2 miles away is going to be a problem. So if you've got lots of people there with mobile phones, with Wi-Fi, with all the rest of it, even microwave ovens, that is a huge problem. You add satellites to the mix, and the more and more satellites you have, we've been picking up iridium for years anyway, at 1.4 gigahertz, but you start putting more of these things up there, you start 5G in the C-band part of the spectrum, it just starts to wipe out a lot of the frequencies that we use for radio astronomy as well. And it's the equivalent of shining a floodlight down the front end of your telescope in the optical. It has the same effect on the radio when you get one of these satellites passing over, shining a beam onto the telescope. So yes, in short, yes, we are already seeing the effects of this, and it's going to only get worse.
Thank you.
Megan, is it inevitable that domino effect that you described, where one satellite hits another and then they, until eventually the whole satellite network seems like would be wiped out completely?
Yeah, it's certainly a risk.
Is that an
Sorry, go on.
inevitable? Is that something that inevitably, I can't say the word, will occur?
So it's again, the more stuff is up there, the more likely it gets. And the experts, the people who do this kind of modeling, tell me that it's almost to the point now where it is inevitable. It will happen. It's just a matter of when. Again, we're already seeing accidental collisions that people didn't predict. There are near misses that people have predicted, and they've been watched very, very closely. But yeah, I think it's inevitable we will see more and more of this happen over the next 5 even years as just more of this stuff goes up there. It's a pretty scary thought, right? Because if it does happen, we do get this Kessler syndrome that creates this, shell of debris around the Earth. We then can't launch anything safely. So we won't be able to launch something like the James Webb Space Telescope. We won't be able to send people to the moon or Mars because it won't be safe for them to pass through that debris field where bits are moving at, several kilometers per second. It just won't be possible.
Megan, when you put together your look back over the last 200 years, you did include spectroscopy. What was your thinking in that, including that?
Well, I only devoted one slide to it. Yeah, spectroscopy was a fantastic invention and has been hugely influential in pushing forward our understanding of the universe. Yeah, you're absolutely right. I mean, it told us.
Well,
Well, thanks anyway for staying up so late with us. That was very kind of you. Thank you.
You're welcome. It's been a pleasure. And as I say, lovely to meet you all, especially get us finally after all these years.
Thank you very much. Have a good morning.
Yeah.
Thank you. Have a good rest of the evening to everyone over there. And yeah, maybe I'll catch some of you on the airwaves at some point.
Could be.
You bet.
you bet.
Take care, everyone.
I put a link in the tweet to, we've got a YouTube channel with a few videos, so we'll post it up there once we get it compiled. But I streamed us live on YouTube after a while, so there you go.
Cool. Great
Yeah.
stuff. Well, thank you very much for hosting.
Appreciate your efforts.
It's been a pleasure.
Good
Good night, everyone.
Night.
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 Good morning.